Once again, welcome to Darlington Locomotive Works. I'm David Elliot. I'm the Director of Engineering for the P2 Steam Locomotive Company, which is an offshoot of the A1 Steam Locomotive Trust, which was the organisation that built Tornado. There's benches at the front here if you fancy a seat. Actually, as he's rather tall, I'll find you another chair out of here. Currently sat in the Stockton and Darlington Railway Company's carriage works, which was built in 1854, right at the end of the independent period of the Stockton and Darlington Railway, when, in common with a lot of railways had started out using contractors to look after their coaching stock, had made the decision to bring the work in-house. As you see, it's not a very big building, but the Stockton and Darlington was predominantly a mineral railway, and passenger trains were very much a secondary feature. It was built very cleverly with built-in obsolescence, insofar as the method of operation was that, and when we have the walk round I can show you this, the way you got vehicles in and out of the shed was through an archway in the side, and there was turntables outside off the tracks that went past, from the connecting to the railway, out at the mainline railway, and then inside the shed was another turntable which enabled you to put vehicles either into this end or the other end, depending on whether they were in for what was basically the clean work, i.e. woodwork and upholstery, or the heavy underframe work, the metal work, which was done at the other end of the shop. This went on for a bit over 30 years, but in 1885 the North Eastern Railway, which by that time had wholly taken over the Stockton and Darlington, built its new carriage works at York. And when that happened, all these odd outstations like this ceased to be used for carriage maintenance and repairs. And after that, the building was basically just used for storage. From about the 1915 or 16 or thereabouts, the field between here and the museum was the scrapyard, became the scrapyard for Darlington Works, locomotive works, which of course is just over the other side of the railway from here on the site that's now occupied by Morrison's. And it remained thus until the end of the works in 1966, during which time again this shed was used for storage. I'm led to believe that there were a couple of Sentinel rail cars kept in here during the war when they stopped using them on the main line. By that time they had got round to putting doors in the end so that you could get longer vehicles in and out. But come 1966 the works closed, the scrapyard obviously went with it, and the building became unused. However, and it remained in that state, it had the odd tenant in it. However, in 1975 or thereabouts, coincident with the Stockton and Darlington 150 celebrations, the station was leased by the council to form the basis of what's now the Head of Steam Museum, and this building was taken over at the same time and actually bought outright by the council. After that, the council let it out to various road motor organisations as garage space basically, but eventually it got to the point where it didn't pass muster with health and safety. One of the good things was that soon after the council got it, they re-roofed it, because in the meantime, both it and the station were listed as Grade 2, so they had to be maintained. The new roof, you can see there's still evidence of quite a lot of fresh woodwork on it. The new roof certainly protected it. However, by the early 90s, as I say, health and safety considerations had meant that it was no longer viable as a business premises, so it was disused. And in 1995, the A1 Trust, which had initially made overtures to Doncaster and the council there, because of course if we look at the A1 locos, 2/3 of them were built in Doncaster, however the other third were built here in Darlington. And after 3 years of attempting to get somewhere in Doncaster, find some premises, and a number of good launch events and things there, but they weren't coming up with any help in terms of finding us premises. We turned to Darlington instead, where the reaction was completely different. Doncaster, at that stage, had been Labour for 64 years. Darlington changes hands from time to time. The consequence is that the council's a lot sharper here. The other thing we didn't know at the time about Doncaster, but after a visit from the special branch, we learned that there was something odd going on in Doncaster, and sure enough, within the next 18 months, 4 councillors were in jail for embezzling money from the organisation. So, not totally surprising, we weren't getting their full attention. However, we approached Darlington and were welcomed with open arms. It helped that the then chief executive of the council happened to be the guy who'd organised the Stockton and Darlington 150 celebrations and was a severe railway enthusiast. And he said, well, we may have a building for you. And we have, incidentally, a target in our structure plan, there in the back of the structure plan under tourism and leisure, was to become the home of a famous London and North Eastern Railway steam locomotive. And at the time we said, we've got about a third of one, would that do? And amazingly they said yes. Anyway, the upshot was over the next 15 months or so, this building was taken from dereliction, had new windows put in, the interior stripped out, the floor lowered, the pit put in, the amenity facilities put in, and oh, joy of joys, industrial standard lighting and heating. We have gas heating here. Now this was regarded at the time as being particularly namby-pamby, this business of having heat and doing heritage railway stuff, because traditionally it's done out of doors and in awful weather. But I have to say, the fact that in the early days in particular, a lot of our support were retired or almost there, and they still are, and me myself's now reached retirement age. Having heat is wonderful, it maintains productivity. There's another useful sideline. If we leave the heating on all the time in the winter at low level all the time, even if we're not here, to prevent the temperature going below about 42 degrees Fahrenheit, you'll see we have lots of bright metal here, and it stays that way because we never let the place go below the dew point. So that's the basis of where we are. Right, now getting around to the new engine. I'll start first. So, brief introduction. That piece of film at the end is the only piece of film we found of a P2 travelling at speed. We've got several bits of moving around depots and a bit of it, one of them in Fife, but going very slowly. Now, why build a new P2? Well, I suppose the thing that isn't really on this sheet on this particular slide is that the chairman and myself always wanted to build a P2. In practice we built an A1 first, which was actually very much the sensible thing to do, because unlike the P2 class, the A1s work straight off the drawings and out of the box. And if you only got to look at their history, then the very little modification work between the birth of the A1s in 1948 and when they were withdrawn in the mid-60s. On the other hand, the P2 has the odd problem or two, which I'll come on to. We were thought to be balmy building a new steam locomotive in 1990 as it was. I think if we'd chosen a P2, we'd have just never been given any credence at all. But we went on and built the A1, proved that it works and works very well, so P2 came along as the next choice. It was the most powerful express passenger locomotive in the country at the time. Certain fraternity from the LMS will point out that the Duchess, in terms of horsepower, produced more on test than P2 did. I'm going to do something about that. We're planning to live up to our claim here. However, they were all 6 of them, there were only 6 of them built, were rebuilt as Pacifics in 1943 and 44 after Gresley had died, and his successor, Edward Thompson, basically had an almost pathological dislike of much of what Gresley did and was determined to make his mark. Unfortunately, his rebuilt engines were really no better than the worst performances of the P2, and had the fundamental drawback that they couldn't haul such big trains because they only had 6 driving wheels instead of 8. It's a big gap in preservation. The procession to the plinth continues. It's getting increasingly difficult, and you've only got to look at Flying Scotsman to keep these old engines railworthy. For a lot of the time after initial preservation, they were living off the work that was done by VR in the late days. You're now in a position where the older and more heavily used engines are needing massive rebuilds, typically £1 million or £1.5 million spent every 7 or 8 years to keep them going. So there is a bit of a reason for building a fresh one, at least where it's not rusted away and we know what the fatigue condition of all the materials on it are. And of course we did have a lot of fun building Tornado. Unless we forget what this is all about. I think you just want to watch this next footage. This is approaching the top of A-skill with about 400 tonnes on the drawbar, producing about 2,400 horsepower at about 55 miles an hour, with just about everything going. One in 100 gradient. Now you will notice one thing about that, in spite of the fact the locomotive was working flat out, the exhaust was the textbook light grey colour. And it's one feature of the later LNER locomotives, and it will affect the P2 the same way, that with its combination of drafting system and exhaust system, it will work flat out without smoking. Because it's able to provide adequate combustion air at all conditions. So, P2 in the 21st century. Tornado will take 13 coaches almost anywhere, but won't take 13 coaches to Inverness or over the South Devon banks from Exeter to Plymouth because of the severity of the gradient. She'll do it all right, providing we don't have to stop, but it's very questionable as to whether she'd be able to restart 13 coaches on the 1 in 40 curvature of the South Devon banks if it's raining. So we are limited to 10 down there, and we are limited to 12, or technically 11, though we have taken 12 to Inverness, where the ruling gradient is about 1 in 60. The P2, with its extra pair of driving wheels, won't have such a limitation, so we can effectively take 13 or even 14 coaches anywhere we choose. We say similar outputs to Tornado. We redesigned Tornado's tender to take extra water at the expense of some coal, so that she now takes 6,250 gallons of water in the tender instead of 5,000. And that gives us 110 miles minimum between water stops. And that is actually quite important when we're on the East Coast Main Line. We are the only engine on the network that can do King's Cross to York with only one water stop. Everybody else has got to stop twice. And we do this fairly consistently when we do this. Normally take water at Grantham on the way up. So that is a significant benefit. It will be a 75 mile an hour engine with a possible increase to 80. But unlike the A1s, which were recorded as fast as 108 miles an hour, the most that was ever recorded with the P2 was 86 miles an hour, so we will have great trouble with the regulatory authorities, notwithstanding anything we can demonstrate in terms of balancing theory, to do more than 80 miles an hour with it. But quite frankly, that's adequate for virtually everything we do. So, why were the P2s built? Well, it all really happened back in 1930 when the LNER introduced third-class sleeping cars. And suddenly there were 2 sleeping car trains a night going to Aberdeen, which were loading consistently to 15 coaches and even more. And the maximum that the top-line engines, the Gresley A3 Pacifics, think Flying Scotsman, were allowed to take to Aberdeen unassisted was 11 coaches, because there are some fierce gradients on the railway there. And in practice, the civil engineer wouldn't allow you to hang another engine on the front of an A3 because the consist was too heavy. So they were using pairs of the North British Atlantics, which is the engine you see on the right. Now, they were known as the miners' friend, as their coal consumption could be astronomical in practice. For an engine whose horsepower is about 2/3 of that of the later Pacifics, it burnt the same or slightly more coal. So you can imagine 2 of them were not an economic proposition. So Gresley was invited to look at the idea of designing an engine which would haul these trains from Aberdeen, from Edinburgh to Aberdeen unassisted. Now, he had a bit of a go at the Mikado, or 282 wheel arrangement, back in 1925, when he built 2 freight engines based on the Flying Scotsman design, but smaller, more driving wheels, specifically aimed at being able to increase the load of coal wagons hauled from New England at Peterborough down to King's Cross from 80 wagons to 100 wagons. And these engines, no problem hauling 100 coal wagons. The big problem was, though, the railway couldn't actually cope with 100 coal wagons in the loops, and the train had to be split to get it into the sidings at Hornsey. So, the LNER, always tight for money, decided it couldn't really afford to make all the civil engineering alterations, so those 2 remained on their own, although they were highly successful. As engines, they were too big for the job, so they weren't multiplied, but the principle was there. 1933, the LNER board gave Gresley instructions to work on the new P2 class, and you can see a couple of photos here. The frames are being cut out by a man with a gas axe, having hand marked it all out, which was the way you, certainly on a prototype, you would start with. And on the right you see a photo of the engineering completion. It looks like they are about to lift it to put the wheels underneath. And by May 1934, the finished locomotive had been wheeled up, painted, very short. And Gresley took the opportunity to try a whole series of new ideas about this. The first time anybody had used a 282 wheel arrangement for an express passenger loco. It was the first time an engine had appeared with 50 square feet of firebox. The earlier Flying Scotsman type, 41 foot or 41 and a half square feet of firebox. It's the first time he used the Killala Chapelon double chimney arrangement, which subsequently went on to 4 of the A4s, including Mallard, and is generally held to be the reason why Mallard was able to take the speed record. They tried an ACFI feed water heater. This is a French device which used a pump to inject water into the boiler, preheating it through a heat exchanger in the smoke box. It was tried a few times in this country. The general consensus was that yes, it improved efficiency because you recovered heat which otherwise went up the chimney, but it was so mechanically complicated that more than offset the improvements in efficiency for the amount of maintenance it required, so they weren't perpetuated. It was the first time that the beautiful sonorous 3-note chime whistle which you heard on Tornado was applied to an LNER Pacific loco. It also had this Lentz rotary cam poppet valve gear, which I will go on about quite a bit later. Poppet valves are essentially like car valves. Normal steam locomotives to admit the steam to the cylinders and let the exhaust out, use pistons sliding up and down in a steam chest past ports. This uses the card principle, where you've basically got a cam driving a poppet valve up and down to open it. Now the immediate beauty of this is you can have a separate cam driving the exhaust as compared with the inlet valves, whereas on a conventional loco, the valve piston is both the exhaust and inlet valve, so you can't have the two timings altered relative to one another. All welded tender. Again, as an experiment, Gresley commissioned the Metropolitan Carriage and Wagon Company in Birmingham to build a tender entirely by welding. It's the first time it was done. And on a lesser note, it was the first application of Eric Gilsan's font for a locomotive nameplate, which the LNER subsequently adopted for all its advertising, correspondence, station names and the rest. And indeed, Network Rail still uses Gilsan's today. So, shortly after it was completed, it was unveiled to the press at King's Cross, and you'll see on the right is Nigel Gresley himself with the bowler on, talking to the Lord Provost of Aberdeen on the front of the engine on its first visit to Aberdeen. Meanwhile, and I'll come back to this in due course, another 4 locos were produced. Well, the first thing that happened was a conventional version of this engine was produced for comparison with piston valves, Walschaerts valve gear, and less of the experimental stuff. And then another 4 engines were built. This time, though, they appeared with the streamlined front end, similar to the A4 Pacifics, like Mallard. They never quite. There was some question about whether the original design of front end would lift the smoke effectively, particularly with this double glass pipe, which produced very soft exhaust. Whereas it had been demonstrated that this arrangement on the A4s was the best smoke lifting arrangement ever fitted to a steam loco, apart from the publicity value that it afforded them. Now, the engineering, he says, that's what we ought to be building. But there's a problem. We rely very heavily on interested people from the general public to fund this locomotive, and whilst the serious railway enthusiasts will recognise that that's a P2, a large number of the sort of passing interested railway type people will confuse that with an A4 Pacific and just say it's a badly built one. And therefore, we need to have this differentiation. We have enough trouble with Tornado being confused with Flying Scotsman. And the front end of the P2, as we are building it and as was originally built, was and is unique. There were only 2 of them ever built like that, and they didn't actually last long in that shape. We are talking with aerodynamicists at the moment to ensure we don't have a smoke lifting problem, making use of the intermediate 70 years of aerodynamic development, so I'm reasonably confident. However, the first 2 engines were rebuilt as streamliners in 36 and 37 to match the rest of the 4 of the class. Now then, in order to make this happen, one of the key things is, are there any drawings in existence? And luckily, the National Railway Museums have got at least 300 drawings associated with P2. Not quite such a full set as we had with the A1, where I reckon we had 95% of all the drawings that were ever needed for it. We've probably got about 70% or thereabouts. But bearing in mind we're having to do a major re-engineering exercise. Here you see my colleagues operating the scanner at York while we were scanning the original drawings electronically, so that we can do things with them. So, one decision that was considerably different from Tornado was the decision to draw the entire loco in 3D CAD. Initially, I wanted to do this because when we built Tornado, it all went pretty well, except for one area, and that was plumbing and electrical conduit work. We did, there's an awful lot more pipe work on Tornado than there ever was on the originals, because we have air brakes in addition to vacuum, and we've got a comprehensive electrical system on, whereas previously Tornado had a very primitive electrical system on, and P2 hadn't got one at all. So we designed all this and then installed it all off schematic diagrams with me pointing at the engine as to where things had to go. And if I was going to be away, I'd chalk on the side of the frames and box goes here with some dimensions, and I'd come back the following day and sure enough the electrician put a conduit straight through the space. And this went on, and in some cases it took 3 attempts before we got the pipework right, and some of it is not right. The electricians in particular have made getting this live steam injector off a job for a tame ferret with a big spanner. It really is a dog's breakfast, and we're not doing that again. So this time I decided we were going to design all the pipework in 3D, and they would get detailed drawings as to where it went, and unless there was an exceptionally good reason, I wouldn't accept it anywhere else. That was it. However, since then, the chairman in particular, who also looks after our marketing, realised what lovely pictures this 3D CAD produces, and you'll see it all over our publicity. And it is very useful in other areas as well. Now, we're going to stick to the original design as far as is practical. As I mentioned, there are some problems with this engine, which I'll come on to. We've also have to change it, make it work on the modern railway. We've got to fit air brakes. We need electrical system. We need all the modern safety equipment, train protection and warning system, the on-train monitoring and recording, the black box, which of course is orange, this sort of thing. And we also have certain other areas where we're just going to improve it anyway. In particular, we're going to use equivalent tornado design where we can, and the LNER, in spite of being reputed for not going in for standardisation, they didn't at locomotive level, but they did at component level. And consequently, up there are probably about 250,000 quid's worth of wooden patterns, and half of them we're using again for the new Loco, which is handy and useful. We also are doing some improvements to help us with day-to-day maintenance and life cycle costs, the most spectacular one being the use of Tornado's roller bearing design instead of plain bearings. But we've also, for example, fitting it with a rocking grate and a hopper ash pan, which greatly facilitates end-of-day servicing. And at the front end, we're putting, as we've done with Tornado, a self-cleaning smoke box, which is a whole series of baffles and grills, which, thanks to some aerodynamics, keep all the char out of the smoke box. They break it into tiny pieces and stick it up the chimney. This is great because we get to the end of a day's activities and we might look in the smoke box, but it's just to make sure nothing's dropped off. If you do decide to go, and you won't get more than half a bucket full of ash out of it, it clears it perfectly. The downside is, if you are one of the inveterate leaners out of the window, like I am, you get grip blasted continuously. So, other things which are really apple pie, materials at least equal and preferably better than the original, and of course we have to achieve compliance with railway standards wherever we possibly can. So, here we have the 3D model of the Loco, showing some of the areas where we've got commonality with Tornado. Now, one thing we have got commonality with is the boiler. The P2 boiler pre-war served as the prototype for the post-war A1 boiler. The firebox is virtually identical. The only significant difference is the P2 boiler is 17 inches longer than the A1 boiler. This means that we're going to use the A1 boiler. And as for the 17 inches, the smoke box you see here is 17 inches longer than the old one, and that closes the gap up. Now people say, oh, won't you lose steam raising capacity? And the answer is no. The research work that was going on in the late 30s and early 40s clearly demonstrated that the optimum length between smoke box and firebox was 17 feet. On the earlier engines it was 19 feet, then it went down to 18.5 feet for the P2. They were getting there. The problem is that front bit of the boiler, by the time the exhaust gases have got there, it's contributing very little to boiling water. And the longer tubes means you have to create a bigger draft to get the fire to burn. So shortening the boiler back, and all the post-war engines this size have 17-foot long boilers between two plates. So there's logic to use Tornado's boiler, plus we know it's just about the best steam raising kit anywhere on the railway today. So the other thing is we own the design rights. We may well go back to Germany to have it made, but we have the choice of making it in the UK. Some more 3D views. in understanding how it works. It's a 3-cylinder engine at the top, and the upper view there shows the crank axle at work. We are also fitting roller bearings, and with them come things called cannon boxes. If you look here, the axles are actually encased in a steel casting from side to side. This economises on bearings. We use tin-pin roller bearings, and they are taper bearings, and they have to be used in pairs to give you end float control. Is that somebody on their way in? By having an axle box effectively spreading from one side, stretching from one side to the other, we only have to put 2 bearings in. In the case of the crank axle, we can't do that, so each of those axle boxes has 2 bearings in, so that's 4 bearings per axle. It was Timken's way of keeping under control the number of bearings that were in use. So, again, the green is stuff that's lifted off Tornado. The turquoise is the cylinder block, which I'll come on to a bit later on, which we're completely redesigning. The red bits were steel castings, which we're modifying as fabrications. We are casting wherever we can realistically do it, and you're making a lot of use of polystyrene patterns, but the problem we've got with big one-off castings is that the pattern cost runs into tens of thousands of pounds, and we only need one at the end of the day. Polystyrene can be used, it's much cheaper to make, but if it's a big, thin pattern, this is using expanded polystyrene, where you make the pattern out of it and then bury it in the mould and leave it there. You pour the steel on the top and it vaporises, because there's only about 1.5% of its actual matter, well, actual solid matter anyway, the rest is gas. But it's not strong enough such that when you pack it up firmly in the mould, it will distort. And we've had this trouble when we were on Tornado trying to do bigger castings that way. So we're going for fabrications. We can use better materials, we can weld to boiler standard with full penetration welding and full NDT, and be confident that it'll be a lot stronger than the original casting was. We also stress relieve before we machine, so we're back to almost the cast condition in terms of metallurgy. That's one thing. Now, the other thing that comes along here is various things we've got to sort out. The engines certainly had a bit of a habit of falling off on tight bends in yards, which was put down to their excessively long rigid wheelbase, which isn't the case, as we've discovered. The pony truck at the front, the 2 small wheels at the front, are suspended using Gresley's patented swing link suspension. Basically, they hang, or rather the locomotive sits on the pony truck through a series of links which are at a different angle, so that as the pony truck moves sideways when you go around a bend, it tries to lift the front of the engine up a bit. And the idea is the extra weight pulls the pony truck back to the middle. The only problem is when it goes right over to full travel, it's attempted to lift the front of the engine 1 7/8 inches, which it won't do because the springs will equalise the pressure. But just at the time when you're on a hopeless bit of track in a yard somewhere and the pony truck's gone over to full travel, you do want the flanges on the leading driving wheels to be doing what they can. So you unload the leading driving wheels and they walk over the top of the rail and fall off. A bit of a problem, so we didn't want that. We got round this this was already a known problem. And the V2 Green Arrow Class 262 express freight engines that the LNER ultimately built about 180 of had the same arrangement. However, in the deteriorating track conditions during the war, they had 5 derailments of these things, where the track was always the primary cause, but they discovered that they felt that the pony trucks contributed. And so they adopted a design from the LMS off their 8F282 freight loco, 280 freight locos that were being built in Doncaster for the war effort, which uses springs instead of swing links. These are much better because they don't lift the front of the engine. As soon as you go slightly offline, it belts about 2 tons of restoring force on them. It goes up to about 3.5 tons as the pony trucks moves over sideways. Just the same arrangement as Tornado's got. Anyway, that plus some tweaking of the lateral clearances in the in the driving and coupled wheels has ensured that it'll go anywhere Tornado does before it falls off. We can go around a 5-chain radius curve with it, which is the worst we should find anywhere. So we'll have the same route availability. In order to demonstrate all this, we commissioned a vampire study which Vampire is the software that the railway industry uses to predict ride and track forces. This is an excerpt from it showing the engine just about to go around a curve which will derail it, and the reasons why it was doing it. The whole lot's modelled accurately on the computer. We had a feeling we were going to need to do this a long, long time ago, because when we tested Tornado, we had to do some limited track force testing, only to demonstrate that it wasn't going to break the rails, and it wasn't any worse than the modern standards allow. But we took a very comprehensive set of track force data by instrumenting the engine on our final test run from Tyne Yard down to York. Now, conveniently, the Network Rail yellow new measurement train had been through the week before, and therefore had accurately recorded the condition of the track from Tyne Yard to York. Delta Rail, who were doing the modelling for us, produced the model of Tornado in software, ran it over the recording of the actual track condition, and demonstrated that Tornado's model was not far off what actually happened, and by tweaking the model about, they actually got it to very, very close to, in reality, what would be predicted from the model's ride output. So that means we've now demonstrated that Vampire can be used for a steam loco. The next stage is to reconfigure the model so it's a 282 with the suspension arrangements that this has got. Have a look at it again. And the result was that it did show that this swing link suspension was causing some strange effects from time to time, but with these side control springs, it was fine. In fact, with that and the other minor tweaks we've done, it now actually rides better than Tornado at speed, which you'd expect with a long rigid wheelbase on an ordinary track, and it doesn't produce excessive track forces when it's going around bends. So, that fixed that one. The next problem we had, the wheels fell off from time to time. The P2 class, in a 10-year period of operations with 6 locos, had 5 broken crank axles, and they always broke just behind the wheel. Now, the likely cause is the same crank axle that the A3 class has in Flying Scotsman's got, but with larger cylinders. Also, 8 coupled engine instead of 6, they don't slip very often, so the peak torques will be much higher. And also there's some design issues as well. That is what came to mind. Another bit of pure good luck. We're having Tornado's axles tested, which we have to do with ultrasonics every 3 years. And the guy who's doing it, not far off retired, and was trained at Doncaster. And when Doncaster was chucking out some documentation, he fished out an album of the rogues gallery of broken tyres, broken crank pins and broken axles. And I'm thumbing, he showed it to me. And I'm thumbing through it, historically interesting. And I cottoned onto that page. There we have 2005 having broken its crank axle at Stonehaven after 133,000 miles, and we've since learned that the youngest one did it at 93,000 miles. Pretty obviously a problem there. But it actually quite clearly, it demonstrates we're now looking at the broken axle end, the wheel should be there. You will see here, there is the end of a keyway. Point it back onto that screen. Oh, there we are. That is the end of a keyway with a fairly sharp corner in it. Crack started there, radiated through about 2/3 of the way through, at which point the loud bang has occurred and the axle's fractured. Fortunately, because it was happening under high torque conditions, it always happened at low speed. You don't get high torques at high speed. Anyway, we obviously can't build a loco that's going to do this. So the next phase is that we commission another study from one of the railway specialists, which in this case was Mott McDonald's at Derby, who have the bloke who's rated as the wheel set expert in the country. Finite element analysis to first of all look at the original design. Then we immediately proposed the Timken design, which is on Tornado, which came with the roller bearings, and had such things as stress relief grooves and a sensible modification to the keyway to reduce the stresses. And that served as far as we got, but it was still not quite giving us what we needed. You can see the original design here with the, I've lost it again. Drawing a mouse, it doesn't appear on the screen. There is the keyway milled with an end mill with a sharp corner in it. This is Timken's solution to the problem, a sledge-shaped keyway, which comes out gradually and stops before you get to the back of the however, they ran it again, and although it dramatically improved the fatigue life, I mean, just to put it into context, the original axle was showing that at the worst case condition of 75% cut-off and full regulator at 10 miles an hour, the life was 900 miles. Of course, we only run for very short periods in that condition, once you're up, and the target's 250,000 miles for this. So at the second iteration, we increased, went back to the usual railway method, made it a bit bigger, and we increased the axle diameter where it goes through the bearing from 9 3/4 inches up to 10 inches. And that suddenly more than doubled the fatigue life again, and has taken us to a point where we're reasonably confident we'd get to 500,000 miles, but we will still adopt the LNER practice of changing crank axles at 250,000 miles. So, problem solved. We've also used the best possible steel axle material, which is stronger than the standard stuff, which helps a bit. At the same time, the crank sweeps, which are the same design as every other LNER Pacific, we've now got EN19 as the material there, so it's significantly stronger than the EN8 that the originals were made from, but still retains good fatigue resistance and is ductile. Of course, the railway industry as a whole hates hard, brittle materials. The idea being, if it goes wrong, you want whatever it is to bend and not to fracture, because rods flying around at high speed which are broken are extremely dangerous. And so we have to keep a very close eye on ductility of materials. Moving on. We're now in manufacturing phase. Frame plates were ordered from Tata back in the beginning of 2014, and we went for a day to watch our frame plates being rolled. We didn't get a lot of joy trying to get Tata interested in this. However, you will notice that we'll call him the new engine Prince of Wales. There's good reason for that. He's very interested in steam and very interested in what we are doing. And after a few weeks of not getting much interest from Tata, our chairman rang the Prince's personal private secretary, who we happens to know, said, "We've got a problem here." Within 24 hours, we had a very senior person at Tata contact us about what we wanted to do. So that's have its uses. And a few weeks later, the plates have now been grit blasted and primed and are now being profiled using their CNC profiling machine. The process being started with the two gentlemen on the right, who are the grandsons of Sir Nigel Gresley himself, still very much in existence. So there's a nice bit of continuity there. After that, the frames went to the Borough Foundry in the West Midlands, who have a 42-foot-long Elgar mill, which we could put them on to do all the crucial machining in one go. Another change from Tornado and standard practice, we have machined these frames all round. Generally, you only machine where you've got something touching. But we found this was very difficult when, for example, setting the foot plating up, because on Tornado, the top edge of the frame is a bit wavy. Not that much, you know, it's been dressed up from flame cutting, but it's not brilliant. And we were trying to set the frames to align in space, and that is always very difficult. This time, we've machined the top of the frame, so we know they're plus or minus 5 thou where they should be, and we simply set the running plate off the top of the frames. The other benefit is, of course, we've machined away any of the heat affected material where the flame cutting's taken place, which will reduce the tendency of the frames to crack in the future. And in due course, a flat pack arrives here in Darlington. And within a couple of days, we've set it up with temporary spacers, lots of bits of pipe, bits of threaded rod with nuts on.
Able to use Tornado's frame stands again, so nice that we didn't have to go and buy a new set of them. And then we come to the interesting bit of putting the little bends in the back of the frame. They narrow down at the back so that the pony truck, which is the car-taxi truck, which is the pony truck at the back, can move side to side without wheels hitting the frames. And the way we achieved this, on the small components, we press braked it. But putting this into a press brake is going to be quite a problem. So we made a template, a former, which is that bit of steel there, which in turn is welded to some other few bits of gas steel, and in turn welded to the rails to hold it in place. Mick and myself warmed the plates up with 2 of these big warm beam torches until they were glowing red hot. And then we simply nudged it with the forklift until we got it round to agree with the template which we made. And then having done that, in fact, we then went to the back of the engine, repeated the exercise, nudging the other way. So we put the dog leg in the frames. I mentioned polystyrene patterns. Here's a significant number of bits which were made out of polystyrene. We've used poly in the past, but it's all been fabricated by hand. This time, we took my CNC, my 3D models, emailed them across to Baker's Patents in Telford, and they have a CNC milling machine which will tape a 2 metre by 1 metre by 1 metre block of solid polystyrene and mill whatever you like out of it. And so all this lot was simply CNC milled straight off the step files which I sent off the 3D. They obviously increased the size of it by 1%, so we got the 1 in 100 contraction allowance, because obviously when the casting's cool, they tend to get smaller than the patterns. However, on the steel castings, for several of them, we used wooden patterns. In the case of the wheels, there's 8, so there was justification for a new wooden pattern. You can see the drag box in the middle bottom there, which is in the engine now. That's a polystyrene one. The horn blocks above, there's 8 of them as well, so they justified wooden patterns. In fact, we used the Tornado ones again. 66 steel castings so far. How? I mentioned we needed to redesign the cylinder block. The P2s were unusual in as much as all 3 cylinders were cast in a single block, monoblock style. And as applied to the P2, there were a number of significant drawbacks. 2 things happened here. Firstly, there were several places where steam and exhaust passed through adjacent passages separated by a single diaphragm wall. That causes the incoming steam to superheat the outgoing exhaust and lose energy in the process. There was another issue in as much as with the poppet valve here, the clearance volume at the end of the cylinder. Imagine your piston slides along travels along the cylinder. There's obviously a little gap so it doesn't hit the back, and there's the volume of the ports up to the valves. You want to keep that to the minimum because any steam in there doesn't actually do anything for you. And the target is, on a modern loco, steam loco, is 8-9%. The P2 had 14% at one end and 16% on the other end on the inside cylinders, which was obviously not good. So I've managed to get it down to about 10%. And then, by duplicating the same valve arrangement as close as I possibly could on the middle cylinder, we've now achieved something like 10% across the engine. Other things though, the other problem we have with cylinders is the width. P2 cylinders, because they were bigger, were wider than the A1 cylinders, and at the moment the A1 cylinders are its tight point on loading gauge, and this is due to the railway progressively moving the track close to the platforms to stop passengers falling down the gap. And so we have to watch this. We can win this back by a mixture of using the higher pressure boiler that Tornado has, which means we can make cylinders smaller for a given power, and also by making them out of steel we can make them thinner, and that gets us the 2 inches off the width.
Traditionally made out of cast iron?
The originals were cast iron, yes, and here is the state we're at with the 3-cylinder design. Not a one-piece casting at the moment, it's a fabrication. The brown bits are cast sections because they're complicated in shape, but being steel we just weld them into the fabrication. And the purple bits are lumps of tube. The rest of it's all cut out of flat, or in the case of the blocks, machined out of profiles, out of solid, CNC machine again. I haven't done it on this scale, but I've produced a very nice set of 15-inch gauge A3 cylinders for an engine that went to Australia by this method. And it's not new. The Germans at Meiningen have been building fabricated cylinders since shortly after the war, and they've got the hang of it. The crucial thing you have to remember is to stress relieve it before you machine it. Otherwise, superheated steam will slowly stress relieve it, and the balls go oval and the pistons don't fit properly anymore. So, I mentioned valve gear. This thing had this poppet valve gear on it. Now, York, disappointingly, have got virtually no drawings of this because the design was owned by the Associated Locomotive Equipment Company, who guarded the design very closely because they made their money by selling sets of valve gears at railways and then selling them spares forever. And if the railways had the detailed drawings, they knew that the ALE knew they'd just make their own spares. So consequently, you never got any more than the odd sort of dimensional installation drawing. However, fortunately, although we've been through the ALE archive, with bits of which are around, there's not a lot of drawing stuff, certainly not applying this early on. Fortunately, about the same time as the P2s were built, they supplied 120 sets of this valve gear to South Africa. And we have managed to acquire copies of the crucial South African railway drawings, so that's given us the missing drawings. Size for size, it's things like the gearboxes and the design of those, they're the same, so we've got drawings for it after all. We are also going back to the original idea of continuously variable cams so that we can alter this cut-off, which is the time you cut the steam off going in the cylinder. Railway steam engines don't have gears, but instead of that, we have variable cut-off. So in other words, when the engine starts, we start with a maximum cut-off, steam being let into the cylinder for nearly the whole stroke. And once we get going, this is obviously very wasteful because you let steam up the chimney still at high pressure. We reduce the percentage of the piston strokes we let steam in for. And by the time we're in the cruise, we're only letting steam in for 15%, letting it expand and give up more of its energy.
It's the entropy of steam, isn't it?
Absolutely, it's a lot of it. Oh, we've got a lot of that on this engine. Yes, we're trying, and the original P2 valve gear did just this, but thanks to the limitations of metallurgy at the time, the cams wore very rapidly on it. Because at times, the cam followers, their corners were resting on the cams, not the flat surface. So, in order to overcome this, Lenz went back to a set of stepped cams, which is the way they'd always done it before. But you only get a very limited number of cut-offs there. And the typical thing is, on Tornado, when we're cruising along, 17% cut-off, come to a bit of a gradient, and the driver will make the smallest control, which is 1% cut-off increase, to compensate for the gradient. Might go 3%. The P2 went straight from 17% to 25% in one step. So you got to a hill, increase the cut-off, which is equivalent to changing down the gearbox. The engine just romps away, and the only way you can control it is partially closing the regulator, and that immediately spoils your economy because you're not using maximum steam pressure. However, we were fortunate in learning about Franklin, who had developed the Lenz gear in the States, and even more fortunate, being put in contact with the son of the man who did the development work, who had his father's archive. There is a set of the Lenz gear on the South African Loco, and here we have a typical drawing of the valve arrangements from South Africa. Now the chap in South Africa, in America, they'd actually fitted it to about a dozen locomotives over there, each a single member of a class as a demonstrator. However, this was in the late 40s when the Americans were dieselising like clouds, so it never caught on. But all the applications they made over there worked very well, and this engine here ran right to the end of its days in 1959, having had the gear on for 11 years, and they never did anything to it. It just worked. So we know that the development worked there successfully. Anyway, as I said, Charles Smith, the guy who had his father, Vernon Smith's archive, duly sent me a load of drawings because he'd had trouble scanning it, and I learnt why when he said 10 feet long. And this is hanging about another foot off the end of it. You put that into the average scanner and it goes for 8 feet and stops. And we overcame the problem by the simple expedient of scanning one end of the drawing, turning it around, scanning the other, and then electronically joining the two bits back together again. So that got us onto that. Now, I've already mentioned that we're using Tornado's roller bearings. We've got all the wheels. In fact, you can see them dotted around here. 8 driving wheels here, and the heap behind has got the tender wheels and the pony and Cartazzi wheels. We have all the tyres in South Devon. However, axles have been running rather late. In fact, the first 2 are just beside my packing case. The Cartazzi and pony truck axle are there. We've just opened it to make sure they're the right shape and check them over before they go off to the assemblers. And the axle and cannon boxes, castings for them are all being machined and having their manganese steel liners fitted at the moment. 3D model of a wheel. Middle is the pattern for the wheel, and the top right's the first casting. The model is actually the driving axle as opposed to the intermediate and trailing ones, so you will see that the old crank pin's rather bigger, but the principle's there. And they are the axle and cannon boxes prior to being sent away for machining. I mentioned that we were going to use Tornado's boiler, which we've already done some development work on to improve its life. In particular, the foundation ring corners, which is where the inside and the outside of the firebox join at the corner, have a habit of fracturing the Tornadoes. They were originally made by machining out of a solid piece of plate. The problem is you've got grain flow in the plate, and the point where we have the maximum stress is in the corner there, whereas the inner firebox expands and contracts. It's flexing that corner all the time, with the grain flow unfortunately running in the position of the highest stress levels. So we've since have forged corners made, with the grain flow running round the root of the groove rather than running longitudinally round the corner. And we've put them on Tornado for the first time with the overhaul last year. And I'm keeping my fingers crossed, but there's no sign of any new cracking starting, so we're hoping we're going to get the full 6-year boiler overhaul life without any changing in between. Next thing, the smoke box was sponsored to the tune of 50,000 by the Gresley Society, who had a bequest, part of which was to build a famous statue, which you may have heard of, involving the non-duck at King's Cross, of Gresley himself. But the other thing was to help any organisation that's building a replica of a Gresley engine. Of course, we happen to be the ones who are doing that at the moment, so it's very useful. And you'll see much of the smoke box is already here. The lifting plates have been made, that's the green bits on here, and we're expecting back from grip blasting any day now. It's a right pig to make. It's egg-shaped. It's slope front, sloping smoke chimney shape. Nothing really fits and works on it easily. And the next thing we come to is making door. Normally you make a door for a steam loco by spinning a tank end and then locally working over the edges to the sharper radius you find on the smoke box door. Can't do that easily with this because it's got a flat top. And although we could have done it from a round one and then done a lot of cutting and shutting, I wasn't confident that we could get the shape right, and this is the face of the engine. It's the thing that most people will see first. So we decided, after looking at other alternatives, including CNC machining it out of a piece of 8-inch thick plate, to go down the traditional process of having press tools made. And the South Devon Railway, which now has the old Prigham boiler works there, and a 600-ton press, duly made male and female presses, which you'll see on the right now, and pressed the thing out of a sheet of core 10. We are using core 10 steel, which is the stuff the Angel and Alta made of, for the whole of the smoke box in order to try and cut down corrosion. Tornado's already lost 4 millimetres out of its 10 millimetres in some places, and that's only 8 years old. Anyway, the result, which unfortunately is upside down at the moment, you'll see in a few minutes, is spectacular. The door frame, another problem. Normally you just gas axe a big washer out of thick steel plate, put it into a vertical borer and machine it to shape. It's not round anymore, so it was made by CNC machining off our 3D model again. The chimney, much the same kind of problem. The chimney's just gone back for some rectification because the machinist hadn't taken quite enough off it for us. But as you can see, it's an awkward shape, which means we have to have a full set of pattern gear. Tornado's chimney, well, one of it, which you'll see up there on the rack, that can be made out of half panels because it's truly symmetrical. This thing has got a sloping flange on it, so if you see from the woodwork on your left there's there's a complete set of that to be able to knock the chimney out of. Wood, just under 7 grand, casting 1,300 quid. Then we move on to again 3D build again, and from the 3D model we produce a laser profiled flat pack which is rolled where necessary, like that. That then is assembled to the condition you'll see it on here. Very briefly, I shall talk on the subject of fundraising. £1 million for this. So far we've got commitments of about 2.2 million. So we've got a way to go. We're hoping to build it in 7 years, which very simple calculations mean 700,000 a year has got to be raised, average. To do this, we have used the same method as Tornado, which is essentially by asking people to donate. Tornado, £5 a month and multiples thereof. An A1 for the price of a pint of beer a week, and in 1990 you could buy 4 pints of beer for a fiver. Not anymore, so we're asking 10 quid a month this time. And you can only just do 4 pints of beer up here for that kind of money. But that works very well, and for this engine we've currently got 770 people who are averaging about £18 a month each. So that's a good start. But the problem is the curve builds up like this and the spend goes that way. So this time the boss came up with the idea of the Founders Club. As soon as we launched the project in September 2013, we invited people to give us write checks for £1,000. And the hope was we'd achieve 100 people doing this by May of 2014. Well, the response was spectacular. Within 4 weeks we'd got 100, and when we closed the scheme in June 2014, we've actually got 367 people, which with the gift aid back, because we're a registered charity and they're nearly all signed up gift aid forms, should be worth 450 grand. So that's really got us going. I mentioned the covenanting scheme. As I say, we're over 770 covenanters as we speak at the moment, and that's growing steadily. The Boiler Club, when we built Tornado's boiler, we launched a bond issue to raise £500,000 to buy the boiler, because you can't buy it in bits, it all has to come in one lump. This time, again, the chairman said, right, let's see if we can put a club together for it. And this time we're looking at £2,000 a pop, although we will take it in 40 payments for 50 quid a month. And we're now up to 103 members on that. In fact, we've just got another one today, so it's 104 now. Which, with their gift aid, takes us the other side of 240,000. So, you know, we're well on the way to being able to buy a boiler outright. And the latest wheeze is, in February, the boss said, want the wheels under the engine by the end of the year. I said, slight problem, the cash flow is showing we're around about £130,000 short to do that. He says, we'll start a little club. So he has. And the new one is the Mikado Club, so that makes it a 282 Mikado wheel arrangement. And he's got a little list. And we're looking for 160 people. This time £1,000. It's got £1,000 to go again, or 8 monthly payments, 125 quid. And we've got 81 signed up already, and that's happened since April. So again, it's a scheme that's working. What we've discovered is this: we think that there is a collecting group out there. You know how when Hornby or Bachman or anybody like that bring out a new version of a Loco, they know they're going to sell at least 500 to the people who have to have everything. And we're finding this with this. We've probably got about 60 people. Every time we put a new scheme out, they sign up for it automatically. So, you know, that immediately means you've got an income stream there. And we're very, very grateful to them, because this is seriously helping us on the way. And we have some commercial sponsorship. Every time Hornby sells a model of their P2, we get a small but useful donation. Craftmaster Paint, who provided all the finishing paint for Tornado on all its repaints, and we'll like to do it again with this one. Timken, selling its bearings at OEM price and providing all the technical support free of charge, which is great. and of course William Cook Cast Products, who are our principal sponsor on Tornado, they have cast all this lot for us. And although they're not doing it quite on the very beneficial rate Tornado was, it's still well worth having. We're getting some very soft payment terms out of them. Plus, of course, they're a top flight company, so we know we can go on the quality. And that ends the presentation as such. At this stage, I'll take questions, but it's probably better if you address questions as we go around the engine, as time is getting on. The away being grit blasted. This is something new to this, which we didn't do with Tornado. Every piece of steel that's going to be painted that comes in here, after we've formed it and welded it, goes out and is grit blasted and primed immediately. With Tornado, one of the big costs during the overhaul was effectively going back to bare metal and painting quite a lot of the engine where the mill scale had not been fully removed and it had started to bubble through as rust. We are fortunate that our fabricator here happens to be our engine painter as well, which is why you'll see the component, that thing there, is just the bit that sticks up there. He's done all the work on it and he's filled it and primed it this afternoon. And he's doing the one on the other side at the moment. The whole engine's got primer on it. Another trick we do, and if we step this way a moment, is when we assemble things, we wet assemble them. This is something I learnt in the aviation industry, which I worked in for 17 years. We found with Tornado, when we had to take the buffer beam off to bore out the middle cylinder, that there was quite a lot of corrosion on the angles and brackets behind the buffer beam. So this time, every time we put anything together, we give it a liberal coating of a red primer on both faces and then clamp it up hard while it's wet. And, well, we'll see what happens, but I'm pretty certain it will considerably reduce this tendency towards rust forming between plates. Most of this engine was bolted together anyway, but there are some places where frame stays were fitted with rivets. We've stopped using rivets, not where we can, not because there's nothing fundamentally wrong with rivets. Our problem is we don't have people who do enough riveting to make sure we get the quality of rivet contact every time. So the whole engine is in fact held together with driven bolts. And there is a countersunk driven bolt. And the technique is that all these holes you see, which were drilled CNC by when the plates were machined, we leave them 1/8 of an inch undersize. We then position the object we want to, for example this bracket. We then drill through a 1/64 of an inch smaller than the nominal inch size, run a reamer through, power reamer, which takes us to within half a thou one way either side of the 1 inch nominal. We have all these made 1.5 to 2.5 thou bigger in the shank than the hull. They are then set about with a jack, or if we can't use a jack, Mick Robinson's number 5/4 copper hammer, which has got 2 foot long handle on it, to bray them in. Once they're in, we then fit, as you'll see here, these ones go in the other way around, a Philidas self-locking nut, which is torqued up to the appropriate torque for the material and the diameter of the bolt.
Wouldn't Cyrogenics do a job easier?
So, yeah, what this is business of chilling it. Yes, the only thing is I'm a bit nervous about that because I have seen some EN8 material which was chilled and then formed cracks.
Heat traction.
Yeah, basically because the problem is the outside chilled faster than anything else. It went brittle and there was a lot of little cracks that appeared. This is actually on an axle for a heritage loco.
Well, there again, 2 holes on shaft on your hammer doesn't exactly.
Well, we're EN16 bolts here, so they're pretty. They're pretty good, and the final pull-in is done by the nut on the back. We've got about 1,000 of these on this engine, and there were about 700 on Tornado. It's got more frame stays in at this point. So, and when we did the overhaul of Tornado in 2014 and 15, there wasn't a single driven bolt that was loose, and that's after 80,000 miles of running. So we think the method is pretty good. It's slightly dearer than riveting, but as I say, it gives you such a reliable and predictable joint it's worth doing. We have to bear in mind that nearly all the bolts on this thing operate in shear. It's not like modern technique where you try to design it so that they're in tension, and where you have got shear condition, you rely on friction but are still putting loose bolts in. These are nearly all working in shear. We've got rivets in a few places like this. It's a secondary fastener. The main reason is that inside here there's a lot of Forester pipework that comes from the back of the engine up here, and if we put bolts with nuts on, they'll get in the way of the pipework, whereas we can do this with nice, neat and tidy snap-head rivets. This is the area where we did the bending using the heat and forklift method, where it just turns in there. The outer frame stage, you can see there's still evidence of the press braking that put the curve in there. The cab is one area where we've gone back to rivets on a big scale, and the reason for this is that whole cab area is virtually completely unsupported. And 5mm plate, and if you start welding anywhere near it, it'll go pillow-shaped. You'll never keep it flat. So we've done the cab traditionally, which brings us on to another of the features which the pre-war LNER locos or earlier ones abound with. Please look at the beading on the back edge of the cab here. Originally it was made out of 2-inch half-round beading, which you could go and buy from any old steel stockholder. Today, it's not made. So the first job we have to do is make the beading. And the method which we use, and if you just follow me around here, it's now a bit more fluffy around here. The method we use, we've got something to put together. What we do is take 2 bits of 2x1, in fact if you look behind you, you can see some prepared, 2x1 rectangular section steel with a 5mm strip between it, bolt it together with bolts which are submerged below the layer of the top of the steel in 6-foot lengths, which we then put in that lathe and turn down till we end up with 6-foot long cups of beading that look like that. Once you've done that, you then rely on the skill of our 2 master assemblers here, Ian and Mick, who hand smith the steel beading to fit the back of the cab, which is already rolled to shape. When you've then got the inner and outer ones, you open the holes out. We use temporary to hold it together in the manufacture. Put even bigger, about typically 1/2-inch bolts with Allen socket heads on them, but are fully submerged below the surface. And then once you're happy everything's tight and it's all in the right place, you weld all the bolt holes up and polish them back, and it just looks like that. Beautiful job, very, very expensive and time consuming to do. Oh, it is, it's compound curvature. I was actually looking at having the compound curvature bit CNC machined out of a lump of solid, at which point Ian, our fabricator, took this as an affront that we thought he couldn't do it. So he demonstrated he could, and I apologised to him and let him get on with it. Things like the window frames here, where there's beading there, they were laser profiled out of a piece of plate, and then Ian hand sanded and ground the radius on them. Previously I'd had them CNC machined on Tornado, but he's so good at putting a constant radius on things that I gave him the chance to do it. It's probably cost as much in man-hours as he would have had it machined, but the result is just as nice. They are actually then plug welded on from the back. I'll just manage to avoid distortion. You'll notice in the back of the cab that the floor is going in. The original cab just had a series of steel legs with supporting bits of angle iron and wood. This one, we need to fit our brake equipment on for the Loco. And we did this with Tornado, where we have this rather irregular shaped cubicle, which gives you, we'd sit wood on the top to make a proper cab floor. This is, this works so well on Tornado, we've just replicated it here. It has the added benefit that it welds the bottom of the cab together. So you will see, when we lift, we put a piece of pipe across there to stop the sides being pulled in. It's not a major problem at the moment, but on Tornado, first time we lifted it without a beam in, there were conduits went up there to light switches and the conduits fractured. So we thought we'd better do something to stop that happening. And we've designed all the connections to the cab, brake gear, nearly all sits in the cab, including the two handles the driver operates. And quite a few of the gauges are attached to the cab. And we can get the cab off Tornado in a shade over 4 hours. Thanks to that, and all the electrics are just disconnected on large multi-pin military type connectors, which is a great asset if you've got a leaking stay in the firebox, because you have to take a cab off to get at most of it. And we've replicated that here. Again, this is a bit more complicated to make than the A1, because although the A1 has bevel-shaped windows, it goes straight across the front. This thing resolves itself at a point, the lid of which is not on at the moment, and actually encases the 2 safety valves. And that's one thing we've had to change. This cab's actually 1.5 inches longer than the one that it should be, because otherwise one of the safety valves would be half in and half out of the V-shaped bit of plate, which would look really awful. And I would be quite pleased if any of the model makers can tell me where we've increased the length. Right, I mentioned the drag box, that was polystyrene pattern steel casting machine, and then bolted on the same method. There's a hardened steel plate goes on here, and then the front of the tender has a centre buffer out of cast iron, and the two of them held together by the drawbar, which has 14-ton static force on it. And this means that when you put maximum output from the engine, by and large the tender still keeps up with it. But more importantly, on the Tornado in particular, the friction between the cast iron block and the hardened steel block, as it slides back and forth, does a lot of stabilising the engine at speed and stopping it tending to whack. And moving on back down this side, we've been very fortunate in as much. I had an outing recently. One of the perks of the job that I do here is that I'm well known in the steam and quite regularly get rung up for advice. And one organisation which has just finished a 35-year rebuild of a southern merchant navy class Pacific Peninsula on Oriental line down on the Gloucester and Warwickshire Railway. We'd given them some tips when they had to make some new brake gear, and I got invited for the inauguration with Pete Waterman rededicating the engine. And I got talking to their chief engineer at the time. He said, I don't know if you're interested, but I've got a Davison Metcalfe monitor 12mm injector, which we don't need, which is the ones we fitted to Tornado. And there it is. It's brand spanking new. That's the box it came in. It was made in 1982, but it's never been used. It was a batch that we used for a series of these southern engines, and they're 10 of them made at the time. Well, we've got three of them now, because Tornado's got one on with a spare, and now we've got one for the P2. And that was a couple of £1,000. We'd have to make that. We'd be looking at the long end for about 15,000 to make it from scratch. So very, very useful that. Plus we've got spares for it. So that really just about takes us showing most of the what we've got to see here. If you've got any questions, feel free to ask.
How many people have we got working on this?
We have right, well we have 2 full-timers. I say they're full-time, they're contractors, who are here full-time. One who's doing the big heavy stuff. It really is the area for the really skilled guys with the heavy stuff.
Are you training the youngsters?
Not at the moment on anything like a regular basis. The hope is that when we get to a 3rd full-time employee, we will take on a couple of apprentices. The trouble is, there's only 2 of them, and especially as being contractors, Ian goes off and paints engines from time to time. He's just painted the Deltic for the National Railway Museum, so we lose him for 6 or 8 weeks at a time when he does that. Mick's building a house on the Isle of Man, and he intends to disappear for 2 weeks at a time. What it means is we can't guarantee the continuity of people on the premises all the time. We also have Gemma, who you'll have dealt with in Turkey, who is our full-time office manager. She was brought in initially as the administrator for the P2 Trust, but she's proved to be so good. She's now the overall manager, office manager for the whole of the A1 Trust. Up till then, we'd done it all with volunteers, but when the P2 came on, the sheer quantity of admin that came about with all the extra covenanters, plus having her on the end of the telephone, which is ever so good on the phone, has won us more money than it's cost us to employ her, which is obviously a good move. The admin just runs smoothly tornado. It hasn't the previous 18 years. So it's been well worth it. But generally speaking, we've just assembled it. You've seen we made all bits of beading and that sort of thing. Most of the work is done the rest of the work is done off-site by specialist manufacturers, obviously foundries, forge masters, pattern makers. We have Northview Engineering over the other side of Darlington here who made all the big frame stays. If you get the chance to put your head in, you can see some of these fabricated frame stays that we've placed castings, where we've also had to modify them to carry air brake equipment. If you look in the third axle hole and look left, you will see that there is a frame stay with an air pump and an air brake cylinder mounted on it. We of course have to fit steam-driven air pumps for this, and I'd like to put them on the side of the boiler where you can get at them, but the aesthetic mob won't let me do that because it does rather spoil the look of it. So we've got two of them between the frames, and we put two on Tornado, which has been a godsend on a number of occasions where we've had an air pump problem and just turned the other one on. I won't talk any more about the one when both of them went, but they are the most unreliable bit of a steam loco, is air pumpery. But we can't get away without them today.
You have a lot of rotating machinery. Our group here is mainly interested in instrumentation.
Yeah.
Do you look for harmonics, vibration, the movement of the various bearings or the shafts?
Yes, we do.
Monitoring it?
Generally, we don't monitor on the loco other than by checking things aren't wearing faster than we think they ought to. The roller bearings are all sized to be such that they're way in excess of what's actually needed for the loads and torques involved. Mm-hmm. So we don't have to worry too much about that. We just have to keep them fully greased all the time to stop water getting in. The big area where we have had to do quite a lot of work is balancing. It's a reciprocating engine. We can balance all the bits that simply rotate, which are coupling rods and the like, and you'll see big balance weights on most steam locomotives, and on Tornado these were achieved the traditional LNER method by casting a big balance weight in and then machining out lots of it to get the balance you require, boring holes in the back of it. We've decided to use the LMS/BR method this time, where we're going to clamp two plates either side of the spokes and then fill the gaps in between with a lead antimony alloy so we can add the balance to get it right. But the whole issue of balancing is interesting, because when we did Tornado, originally class were balanced with 35% of the reciprocating mass, that's the piston rod, the crosshead, and a proportion of the conrod, balanced, which was normal for a three-cylinder engine at the time. However, when we went to talk to rail trackers, it was at the time, and said, what will you accept by way of hammer blow? They looked at us blankly, as nobody there had heard of hammer. Well, they'd heard of it, but they had never had to deal with it today because modern rolling stock has fully balanced wheels. So I explained what it was, and of course what the problem with hammer blow is any weight you add to balance the reciprocating force is doing that. That's the reciprocating forces. That balance weight, when it's at the bottom or the top of the rotation, has got nothing to balance. So when it's at the bottom, it's pushing down due to centrifugal force on the rails, and when it's at the top, it's trying to lift the wheel off the rails. And on two-cylinder engines, where the tradition in the old days was to balance up to 75%, if they get a really bad slip, in fact they actually did some tests to try this out, the wheels will lift off the track when the balance weights are at the top, if you let it overspeed. Anyway, the upshot was we were very lucky to have a bloke who in his youth balanced diesel engines for ships, so understood the maths behind it. It's a great relief, because I don't. And he worked out that if we were going to get the total hammer blow at 90 miles an hour, which was and still is our target speed for Tornado, to be limited between the static axle load, typically about 22.5 tonnes, and the maximum axle load that the railway will tolerate today, which is 25 tonnes. If we can keep that total hammer blow down to 2.5 tonnes per side, because of course it's not doing it all in the same place, they would accept that. And we calculated that by reducing the reciprocating balance from 35 to 17%, we achieved that. Now, the reason why you don't want to eliminate it altogether is that This balance is trying to balance the reciprocating forces, which are big inertia loads, especially at high speed. If you don't balance it at all those forces have to be resolved through the frame of the loco, and that batters the frames in due course. Fortunately, we've got these big, heavy, one-piece cast horn blocks lined with manganese steel plates on the horn block and manganese steel plates on the axle boxes. And even on some engines, for example, the Southern Pacifics, the Merchant Navies and the Battle of Britons, and the Duke of Gloucester have no reciprocating mass balance, but they've all got these manganese liners and they'll put up with this battering. This has got it. Well, anyway, in the end, we put it down to 17%. It doesn't seem to materially affect the wear rates, and it does mean, and we were able to verify this because Network Rail have things called wheel checks installed at strategic places around the system, which is 60 feet of rail with vertical instrumentation under it every few feet. And it's designed to catch freight vehicles with bad flats on, which the owner doesn't know has got a flat on it. And it will send a little raising alarm in the signal box if you're producing big knocking effects on the track. And we used that, and we ran this over the wheel checks a couple of times at various speeds, and determined that it's actually producing almost exactly what our man with his spreadsheet predicted, so we know we're in on that. But areas where I do want to do instrumentation in the future, if anybody feels like getting involved, is we want to put strain gauges on our drawbar so that we can actually compute continuously drawbar horsepower. That's the key area, but that's quite an interesting one because we've got to do it in somewhere. Drawbars don't get a very kind life, so we've got to do it in such a way that strain gauges aren't just simply wrenched off by the drawbar flapping about. So, yeah, but there are other instrumentation things we're looking at. Mm-hmm. We're putting a lot more in the cab this time. We're going to have superheat temperature gauge for a start, which because that tells you how efficient, whether you're in the efficiency regime. I mean, when we speak efficiency, on a good day, these things do about 6.5% thermal efficiency. You know, that's a cull into useful horsepower at the drawbar.
You've got 3 cylinders. Is it triple expansion, or is it
no, it's only single expansion.
Just
yes.
three
same size cylinders.
So that's why your efficiency is right down.
That's right. Yes. Well, there's that. We can't recuperate. We can't go down to a vacuum at the far end like a power station does.
No condenser.
We're no condenser. We can't really optimise the cylinders because of the wide range of power and torque they're expected to produce. So you just have to settle for that. And as I say, the actual cylinder efficiency is probably about 10 to 11%, but by the time we've lugged the loco around, and on a typical train, we're a quarter or a third of the weight of the whole train. I mean, the cylinder horsepower to do 2,400 back end, which we know, by calculation, we know that Tornado does, is going to be around about 293,000 horsepower, and the bit in between is what's moving the engine. So it's a big... It's completely hopeless economically. That's why we're shoveling 70, 80 pounds a mile when we're going up a steep hill, and boiling 50, 60 gallons of water a mile when we're going up, when we're working hard.
So where will you be putting all your electronics? Will it be in the cab or in the tender?
On Tornado, we put nearly all of it in the cab, but we have a new challenge with this one, and retrospectively with Tornado, called ERTMS. That's the European Railway Traffic Management System, which is in-cab signalling. It does away with line-side signals, which means we have to have a huge amount of electronics on board, which of course the industry has simply designed as a 19-inch rack, which doesn't fit anywhere really. And so we are scheming a cubicle in the back of the tender. The benefit is most of the time it's water cooled, so it doesn't overheat. But basically, which it will look from the outside the most obscure door we can make, so it doesn't look like a door. But when you open it up, there's just a series of 19-inch racks to take the new kit. And while we're at it, we're going to move the present on-train monitoring and recording gear and the train protection and warning system, which we still have to have even if you've got the new ERTMS onto the tender, so that if most of the electronics is concentrated on the tender then, which will slightly declutter the cab a bit. I mean, we've still got to have all the man-machine interface and all that sort of stuff. But luckily we took a student on from Network Rail about 6 years ago when ERTMS was talked about, and looking at putting this onto a heritage vehicle. And we've got a lot of photographs of him holding up cardboard boxes representing the various bits that have got to be in the cab. I came to the conclusion it could be there. Also because Tornado is unique out there in the steam fleet as having its onboard, full onboard generation. Most of the steam locos take a battery pack, which they charge up every day to power this lot. But it's because we were starting with a clean sheet. We've got a 900 watt turbo alternator on, which produces 28 volts. And we've also got a 5 kilowatt coach alternator under the tender, which we've turned down to a maximum of kilowatts so it doesn't burn the wiring out. We have 2 sets of batteries on the thing, essential and auxiliary. The essential powers all the safety systems and the headlamps. The auxiliary does the underframe lighting and the poser lighting and various things like that, which if you lose it's not the end of the world. But it's designed, they're fully independent normally, but if we have a battery failure or some other failure, we've got a changeover switch so we can stick the whole lot onto one or other battery set. And so far it's proved pretty reliable. And we've got the capacity to put the RTMS on as well.
Unlike a heritage locomotive, you can actually build TPWS straight into the vehicle.
Well, we had to with Tornado, it went in from new. I mean, it's no different to the heritage fleet. They all have to do this. Unfortunately, they've designed most of the bracketry, so we just copied it. You know, there's nothing magic about this when we put it on Tornado.
I'm thinking the one that overran at Wootton Bassett.
Yes.
Because they made it so that they could defeat it, couldn't they?
Oh, well, we've always been able to do this, because at the time it was assumed nobody would do that. But they did. And unfortunately they had a signal passed at danger, which may have happened anyway, but in reality was quite a bit worse because of the fact they'd isolated the system. I mean, the difference is you will now find that whereas beforehand the isolation valve just had a valve on the floor with a flimsy little plastic telltale on it, it's now got a big lump of angle iron which you have to unbolt first before you can rotate the valve to isolate it. This means you've got to have stopped to do it to get the Allen key out of the coach to be able to undo it.
What's been your own background as to...
Ah, right. Well, I had a misspent youth chasing trains. My father's a mechanic, which helped. I spent my childhood evenings reading about steam, but not just the sort of albums, but I was very interested in the technical books. And I spent my boring lessons at school drawing steam engines. And I was being warned by both my peers and my teachers that it was a complete waste of time. It was old technology was going out. However, I'm pleased to say 30 odd years later it's proved very useful. But no, I then ended up on a degree training course with BR in mechanical engineering based at Derby. Did the degree at Bradford University, spent 3 years after that working BR, ending up as a traction maintenance engineer running the maintenance side of the small loco depot near Glasgow. Saw the light on the railways in the late 70s and decided that didn't like the look of the future of it, so got out and did an MSc in air transport engineering and went into the aviation industry for 16 years, although I spent most of that marketing and doing selling work because it paid better than the engineering. When privatisation took place, I came back into railways with Adtran Signal down in Plymouth as a project manager, which I did for 3.5 years until this organisation, which I'd been the technical director of since about I joined in 1991 and I took over the technical reins in 92. By 2000, Tornado was up here. We were getting contractors in, but there was nobody to supervise them, so I made them an offer that if they could give me something like a half-time contract, I would move from Plymouth to Bishop Auckland so that I could be here and monitor it. And for the first 5 years I was going out and getting on bits of contract work for the railways on various projects. And then in the beginning of 2005, we signed the contract for the boiler and the trust asked me to go full-time, which I did until she was finished at the end of 2008. I then have been working for various other people and still doing odd bits for the trust. until this was launched, when I was asked to get on with the design of this. And now, well, it's already up to full time. And if it's anything like Tornado, within the next couple of years we've gone to time and a half, and by the time we finish it'll be double time. Right, okay, well, thank you very much.
Much for a very informative and enthusiastic presentation to us. On behalf of the Institute of Measurement Controls,
Oh, thank you. The tie. Oh, it's a nice colour, I don't mind wearing that.
thank you very much.